To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today also I am going to discuss some more extra questions related to electromagnetism. So in the previous chapters also we have been discussing extra questions. You all are familiar with the lesson, so I'll move on to the questions. I'm sure you will answer the questions by yourself first and then you will compare your answers with my discussion. So then, extra question 11. First one. What is the rule used to determine the direction of the current in electromagnetic induction? So there needs to be a magnetic field, and when the magnetic field is constant, the conductor has to move between the magnetic field so that there will be a magnetic flux. Or else if the conductor is kept at rest, then the magnet has to move. So you can remember the alternating current dynamo and the bicycle dynamo. In the alternating current dynamo, the wire loop or the armature rotates, whereas in the bicycle dynamo, the magnet rotates. So either way, when magnetic field conductor is there, there is movement so that there will be magnetic flux. Then there will be an electromotive force induced between the ends of the conductor, between the terminals of the conductor. So that is how we have the electromagnetic induction. So the induced electromotive force gives rise to a current flow. And this current flow has a direction that can be determined using the Fleming's right hand rule. So you can remember that also, the Fleming's right hand rule. You have the thumb, first finger and the middle finger, index finger and the middle finger perpendicular to each other. You have the direction of motion by the thumb, direction of the magnetic field, the index finger. Then the middle finger will point to the direction of the current flow. So that is how we find the direction of the current. So what is the rule used to determine the direction of the current in electromagnetic induction? That is Fleming's right hand rule. Fleming's right hand rule. Right hand rule. Then, now this particular current is induced current. Second question, write the factors that affect the induced electromotive force. So from the induced electromotive force only there is a current flow. And there are three factors that determine the magnitude of the induced electromotive force, or that affect the magnitude of the induced electromotive force. What are they? The length of the conductor, or the number of turns or windings in the conductor, because usually we make it like a coil. So we can say the number of turns or windings in the coil. Then the strength of the magnet, and also the speed of movement of either the magnet or the coil. And all three factors are directly proportional. When they increase, the induced electromotive force also increases. So the three factors are number of turns or windings of the coil, strength of the magnet, and the speed of movement of the coil or magnet. Because you all know, students, when the coil is stationary, the magnet moves. When the magnet is stationary, the coil moves. So either way, there will be a magnetic flux that will induce an electromotive force that will again lead to the current flow when it is a complete circuit. So you are familiar with that. So the factors that affect the induced electromotive force are number of turns or windings of the coil, strength of the magnet, and speed of the movement of the magnet or the coil. So with that, students, I am going to move on to the next question. Extra question 12. The first part, Fleming's right-hand rule is illustrated in the diagram given below. Write what is indicated by the 3 fingers. So this is the Fleming's right-hand rule. Here you can see this is how they have shown the hand. There you can see the thumb is actually the direction of the motion. So this is the direction of the motion, whereas the index finger will be the direction of the magnetic field north to south, and then the middle finger will be the direction of the current flow. So we can write it here. Thumb, direction of motion, then index finger, direction of magnetic field, index finger, thumb, direction of magnetic field, and the middle finger, direction of current flow. Or direction of current. If you all want, you can write it on this also. This is the motion, then it is the field and current. Like that also we can indicate. So thumb is the direction of motion, index finger direction of magnetic field, and middle finger direction of current flow. That is the right hand rule, Fleming's right hand rule. I'm sure you have written that correctly. With that, I'll move on to the next question. Extra question 13. Dynamo is an application of electromagnetic induction. I'm sure you all can remember that, students. The dynamo, moving coil microphone, even the magnetic cards, the bank cards, debit card, credit card, employee cards, all these are based on electromagnetic induction. So, what type of current is generated by a dynamo? You all know, because of the rotation, the current that is generated is going to be an alternating current. Because the way the electromotive force is induced and the current flow, the direction changes, so that it is an alternating current. So, alternating current. Or you can even write it as AC, alternating current. What type of current is generated by a dynamo? Alternating current. Then the second one, plot the graph for the current you mentioned above. So to plot the graph, you all can remember, students, we have the axis, so here this is time, and this can be either voltage or current. Then you will see the graph is like that. You will get the positive current and the negative current. Direction of current flow will change with time. So, plot the graph for the current you mentioned above. This is how you get the graph. I'm sure you all can remember that. So, with that, I'll move on to the next slide. Extra question 14. A bicycle dynamo is used to light the bulb connected to the handle of the bicycle. So, you are familiar with these, students. The bicycle dynamo functions based on electromagnetic induction. So, you can remember there is the bicycle tire, the bicycle dynamo, there is a rough head that is in contact with the bicycle tire. So when you ride the bicycle, the tire rotates. Then the rough head that is in contact with the tire, that also rotates, and that is in turn connected to the magnet by a rod. So the magnet also rotates inside the dynamo. And you all know there is a soft iron with the wire coil around it. So there is electromotive force generated in that wire coil. So that gives rise to a current flow that is connected to the, or that is applied to the external circuit where you have the light bulb. So the bulb will be placed in the handlebar, the front of the bicycle, so that light can be shown. Then what happens is when you ride the bicycle, the bulb will light. So that is how the bicycle dynamo functions. So here you all know the dynamo electromagnetic induction. It is the alternating current that is generated. The way the dynamo functions. The EMF, that is the induced electromotive force, the direction changes. We have discussed that before also. So there it is the alternating current. So if we look at the first question, what is the type of current generated by the bicycle dynamo? That is alternating current. Alternating current. Earlier also I told you all students, you can write it as alternating current, or you can say AC current, alternating current. Then the second question, write the energy conversion taking place in a working bicycle dynamo. What is the energy conversion? When you ride the bicycle, there is kinetic energy, that means there is mechanical energy. From the mechanical energy, there is electric energy produced, generated. So mechanical energy to electrical energy. Mechanical energy, nickel energy to electrical energy. Mechanical energy to electrical energy. Then the third one. Why does the brightness of the bulb increase when the bicycle is pedaled faster? Now you all know there are three factors that affect the induced electromotive force. One is the number of turns or windings of the coil. The other one is the strength of the magnet. So in a bicycle dynamo, once it is produced, these two do not change. The magnet is the same, so the strength of the magnet doesn't change, and the number of turns in the coil also doesn't change. So only factor that affects the EMF induced is the speed of rotation of the magnet. That depends on the speed of riding the bicycle. When you ride the bicycle faster, the tire will rotate faster. So the rough head of the dynamo will rotate fast and the magnet inside will rotate faster. Therefore, there will be greater electromotive force induced. That will give rise to a higher current flowing through the circuit. Therefore, the bulb will be more bright. The brightness of the bulb will increase. So, that is the explanation that you need to give here. Why does the brightness of the bulb increase when the bicycle is pedaled faster? When bicycle is pedaled faster, the head of the dynamo, I'll say when the rough head of the bicycle dynamo rotates faster. Therefore, then the magnet also rotates faster. inducing a higher electromotive force. Electromotive force. This gives rise to higher current supply to the bulb. Then the brightness of the bulb increases. Of the bulb increases. So that is what happens. Here, when bicycle is pedaled faster, the rough head of the bicycle dynamo rotates faster. Then the magnet also rotates faster, inducing a higher electromotive force. This gives rise to a higher current supply to the bulb. Then the brightness of the bulb increases. So if you want here, initially you can also mention the speed of movement of the magnet increases the induced electromotive force. But with the explanation, that understanding can be obtained. So that is the answer to this question, students. So with that, I will move on to the next slide. Extra question 15. A transformer circuit is shown in the diagram. So here you can see a transformer circuit. You can see this is an alternating current source AC. Then the primary coil is shown and 50 turns. They have mentioned the number of turns. You all know this is the primary coil. Then these two lines indicate the soft iron core. Then you have the secondary coil. From the diagram itself, you can see less turns in the primary coil, more turns in the secondary coil, and also it is mentioned 500 turns. So obviously you all know it is a step-up transformer. Step-up transformer, the voltage is increased. Now here it is the secondary coil. Then you have the resistance or the load there. So input 50 turns, output 500 turns. So it is a step-up transformer. Right. So the first question, which type of transformer is the above? Explain your answer briefly, but I mention now. Step-up transformer. So here you can say, now this also functions based on electromagnetic induction. The electromotive force depends on the number of turns. So here we can say the turns in the secondary coil is more than primary. Therefore, the voltage output will be higher than voltage input. So that is the explanation given there. It is a step-up transformer. The turns in the secondary coil is more than primary. Therefore, the voltage output will be higher than voltage input. Then the second one, write 2 instances the above transformer is used. Now you can remember, students, in the power plants where electricity is generated, there is alternating current generated, but for transmission, it is always efficient to transmit the electricity with high power. So because of that, you all can remember the voltage is increased to 132 kilovolts or 220 kilovolts. 132 kilovolts or 220 kilovolts. So to do that, they need to use a step-up transformer. That is one instance where we use the step-up transformer, right? Two instances, the above transformer is used. In addition to that, electrical appliances like microwave ovens and X-ray generators, they need high power. So there also the voltage needs to be increased. So there will be a step-up transformer. So those are the instances where the step-up transformer is used. So here, increasing the voltage 132 kilovolts or 220 kilovolts before electricity is distributed to the sub-centers from the power plant. So increasing the voltage, that is to 132 kilovolt or 220 kilovolt before electricity is distributed to the sub-centers from the power plant. That is one instance. Then the other instance is in appliances like microwave ovens and in X-ray generators. So microwave ovens, you all know, we use it at home. X-ray generators, to get the X-ray photography, we need to use X-ray generators. So in those instances also, the voltage has to be increased. So those are two instances. You all can understand that. So that is the step-up transformer. With that, students, I'll move on to the next question. This is the third part of the question, the same question. So you all know 50 turns, 500 turns, step-up transformer. Third one, write a relationship between the number of turns in the primary coil, number of turns in the secondary coil, input voltage and output voltage. So you all know number of turns in the primary is denoted as NP. Number of turns in the primary coil is number of turns in the secondary coil V primary input voltage, Vs output voltage. So to write the equation, we have N primary over N secondary is equal to V primary divided by V secondary. That is the relationship. Number of turns in the primary coil divided by the number of turns in the secondary coil is equal to the ratio between the voltage of the primary coil and the voltage of the secondary coil. So the ratio between the turns is equal to the ratio between the voltage difference. Is that okay, students? So that is the equation. So with that, I'll move on to the next slide. Then fourth part of the question, a voltage difference of 230 volt is supplied to the primary coil. Find the voltage difference of the secondary coil. So here students, you all can remember when we use the equation NP over NS equal to VP over Vs, we can rearrange this equation. Then you will get it as V secondary over V primary is equal to N secondary over N primary. So if we substitute in this, V secondary divided by the primary voltage 230 volts is equal to the ratio between the turns. Now secondary coil has 500 turns and the primary coil has 50 turns. So there, if we do the calculation, you will get V secondary is equal to 500 divided by 50 into 230. Or you can simplify it here. You all know 500 divided by 50, 10. So 10 into 230 volts, or you can rewrite and then simplify. So 10, that is going to be 2300 volts. That is the output voltage. Step-up transformer, the voltage has increased. And before also students, when we discuss the other questions and even during the lesson, I told you all, you can look at the ratio between the turns. Primary is to secondary, 1 is to 10. 50 is to 500 is 1 is to 10. That means the voltage also is 1 is to 10 ratio. Primary voltage is to secondary voltage 1 is to 10 ratio. So primary voltage 230, secondary voltage 2300 volts. Like that also you can calculate, but for a question like this, you need to show the working. You have to write the equation, you show the substitution of the values, and you need to do the calculation. But for an MCQ, you can just consider the ratio. So here, just to confirm or check your answer, you can use that method. Is that clear, students? So with that, I'll move on to the next slide. So here we have the fifth part of the same question. If a 2 ampere current passes through the primary coil, calculate the current in the secondary coil. So how do we calculate the current? We use the power. Now earlier in the question, you all can remember 100% efficiency, or else we need to assume that it is 100% efficient. There is no energy loss. That means the power input is equal to the power output. And power, you all know, is voltage into current. So from that we get the equation V primary into I primary is equal to V secondary into I secondary. So 2 ampere current through the primary coil, though we need to calculate the current through the secondary coil. So primary potential, you all know, is the 230 volt potential into current 2 amperes. That is equal to secondary potential 2300 volts into secondary current. So here, if you calculate I secondary, 230 into 2 amperes divided by 2300 volts. When you simplify these two, this becomes 10. Therefore, the current becomes 0.2 amperes. That also you know, students. In a step-up transformer, the voltage increases, but the current decreases. Why? Because the power remains the same. Power input is equal to power output. So here you can see the current decreases. So the ratio between the current is the other way. If the voltage primary is to voltage secondary is 1 is to 10, voltage current primary is to current secondary is 10 is to 1. You have to remember that. So the current decreases. Then a direct current of voltage 12 volt is supplied to the primary coil. What is the voltage in the secondary coil? Explain your answer. Now here look at the question. A direct current. Look at the question. A direct current of voltage 12. Now, does the transformer function when direct current is applied? No, because with direct current, there is no magnetic flux. Then there is no induced current. Electromagnetic induction occurs with alternating current. So, the output coil, the voltage will be 0. So, output voltage is 0. There will be, the transformer will not function. Why? Transformer will work only with alternating current or changing direct current. Now this part, changing direct current, you can remember when we did the activity, we connect batteries, batteries generate direct current. But what do? We turn it on. As we turn the switch on, we saw that there is a deflection in the galvanometer. That is to understand electromagnetic induction. But when you keep the switch on, there is no deflection in the galvanometer. So that means there is no function of the transformer. Then again we open the switch or off the switch. Then also you see a deflection. So only when you turn on the switch and turn off the switch, or close the switch and open the switch, there is magnetic flux, therefore there is induced electromotive force. But when you supply continuous direct current, there will be no change. The galvanometer reading will be 0. That is why the output voltage will be 0. A direct current of voltage 12 volt is supplied, output voltage will be 0. The reason is transformer will work only with alternating current or changing direct current. So 12 volt is not changing direct current. So therefore the output will be 0. So if you want, you can include that also in the answer. But the transformer will not work with 12 volt direct current. So you can understand that. I'm sure you all can understand this answer. So with that, students, I'll move on to the next slide. Extra question 16. Figure given below shows a model prepared to illustrate the function of a direct current motor. Now this is a direct current motor. The fan rotates when the switch is closed. So if we look at the diagram, you all can see here. Now this is the fan, they have shown that. Then you can see this is the wire loop. Then the north and south poles are given. The magnetic field lines are shown. Then P and Q, you can see the split rings, the commutator rings. And then the brushes are connected to that. And there you can see the open switch and the batteries. So when you close the switch, the fan will rotate. Right. So if we look at the questions. What is the component labeled as P and Q? They are the split rings or the commutator rings. So here I will write them as split rings. So the component labeled as P and Q, it is the split rings. Then here you can see how does current flow in the above setup, direction P to Q or direction Q to P. Now here, if you look at the diagram closely, you can see this part is the positive terminal of the battery. So when you close the circuit, current has to flow to Q, then through the loop through P. So the current flow is going to be from Q to P. P. Q to P through the loop. Through the wire loop. So that is the direction of the current flow, Q to P. You can understand that. Then the next question, part 3. What is the law used to determine the direction of rotation of the fan? For that we use the Fleming's left-hand rule. Fleming's left-hand rule. Fleming's left-hand rule. Then, so here it is actually rule. Fleming's, you can call it the rule. Fleming's left-hand rule. Then the fourth one, write a modification that can be done to change the direction of rotation of the fan. So initially the fan will rotate in one direction. We can change the direction of rotation of the fan by doing two things. One thing, we can change the magnetic poles. You can interchange the magnetic poles. Otherwise, you can change the direction of the current flow. You change the terminals of the battery. So in this activity, you can change the terminals of the battery or can say interchange the poles of the magnet. So when we say interchange, you all know the north will go to this side, south will come to this side. So you have to only do one change. If you do both, then again the fan will rotate in the same direction. You can remember that. So always to change the direction, you only need to do one change. Either you change the terminals of the battery or you interchange the poles of the magnet. I'm sure you all can understand that. So you can write just one answer. I have written both so that you know what we need to do. So with that, students, I'll move on to the next slide. Here we have extra question 17. A transformer circuit is shown in the diagram. So here we have a transformer circuit. Now here you can see primary coil, it says 240 volts. That is an alternating current. Then you can see here the number of turns in the coil, it's more here. Then the 3 lines indicates the soft iron core. Then you have the secondary coil. So you know this has to be a step down transformer. Here they have shown this as 12 volts. So 12 volts, 240 volts. So that means it is a step down transformer. Then first part, what is the basic phenomenon used in a transformer? It is electromagnetic induction. Electromagnetic induction. Electromagnetic induction. Then, there are 100 turns in the input coil. How many turns should be there in the output coil to obtain the voltage mentioned in the figure? So to do this, you need to use the equation. Number of turns in the input coil. So NP divided by NS equals VP divided by VS. So there are 100 turns. We don't know the number of turns in the secondary coil. The voltage, you all know, input 240 volts, output 12 volts. So the ratio between the two is 20. So if you need to find the number of turns in the secondary coil, you can see we rearrange NS is equal to 100 divided by 20. Only 5 turns need to be there. So 240 is to 12, you can see 20 is to 1. That means when you have 100 coils, you need 5 coils in the secondary coil. 5 turns in the secondary coil. 100 turns in the primary coil, 5 turns in the secondary coil. Is that okay, students? So the ratio you can use to confirm your answer. 240 is to 12, so 100 is to 5. Then, write an instance where the above transformer is used. Step down transformer. Step down transformer. So you can remember, students, initially from 220 kilovolts, the potential is reduced to 22 kilovolts. And then from 22 kilovolts, it is reduced to 230 volts. So there are 2 instances where the step down transformer is used. So here we can say, before electricity is supplied to the household, the voltage is decreased. That is from 22 kilovolt to 220 kilovolts to 22 kilovolt, and from 22 kilovolt to 230 volts. So there are 2 instances or 2 places where the voltage is reduced. Initially from 220 kilovolt it is reduced to 22 kilovolts, and then from 22 kilovolt to 230 volts. That is how it is distributed to the household. So that is the step down transformer. The circuit is given, then you all know it functions based on electromagnetic induction. Then we found the number of turns in the secondary coil as 5, and then you all know where it is used. So with that, students, I'll move on to the next slide. Extra question 18. The transformer shown below is used to obtain a 23 volt current from the household supply of 230 volt current. So here you can see from 230 volt current power supply, they need to get 23 volt current. So there you all know input current is 230 volts, output has to be 23 volts. So the transformer that is going to be used should be a step down transformer. And here from the diagram also you all can see, students, this is the primary or the input coil. So in the primary coil you can see the number of turns in the primary coil is more and the number of turns in the secondary coil is less. So it is a step down transformer. Now if we look at the questions, first one, which type of transformer is this? So it is a step down transformer. Step down transformer. Step down transformer. Then the second one, there are 4,800 turns in the primary coil. How many turns are there in the secondary coil? So we need to find the number of turns in the secondary coil. To do that, you all know the equation. N primary divided by N secondary gives rise to voltage primary divided by voltage secondary. So here we know the voltage values. We have the number of turns in the primary coil. So we can rearrange this equation. Then what do we get? We can use the same equation and then we can do the calculation. So you know the number of turns in the primary coil 4,800, but we don't know the number of turns in the secondary coil. The primary voltage you all know is 230 volts and the secondary voltage or the output is 23 volts. Now here students, by looking at the ratio between the voltage itself, you all can get an idea. Primary is to secondary, 230 is to 23, that is 10 is to 1. So the same way, the ratio between the number of turns in primary and number of turns in secondary also has to be 10 is to 1. You all can remember that relationship. But if we do the calculation by rearranging, you will get 4800 divided by 230 volt into 23 volts is equal to N secondary. So here, if we simplify, this is going to be 10. So here, you will get the answer as N secondary is equal to 480 turns. Is that okay, students? So here we have the number of turns in the primary coil as 4800. The voltage that is given to the primary coil is 230 volts. The voltage obtained from the secondary coil is 23 volts. So we needed to find the number of turns in the secondary coil. So that is going to be 480 coils. Is that clear? So here we use the equation and get the number of turns in the secondary coil. I am sure you all have done that correctly. So with that, students, I'll move on to the next question. So extra question 19. Given below is a figure of a setup prepared by a group of students for an activity to illustrate electromagnetic induction. First, the students move the lever vertically upwards. Then they move the lever horizontally back and forth. So we'll look at the diagram first. Here you can see this is a galvanometer, a center zero galvanometer that is connected to a rod. So it says copper rod. So continuous connection is given there. Then what they have is a magnetic poles, the north and south poles of the magnet you can see there. Then there is the PVC tube connected to a lever X. So inside there is the copper rod. So you can see, you can understand from the diagram, students, there is a copper rod that is connected to the wire and that is placed inside the PVC tube. So PVC tube is an insulator. The PVC tube can move within this particular handle-like structure. So PVC is an insulator. So there will be no connection between the copper rod and this particular handle. So if that handle is also a metal, if you don't have the PVC tube, there can be a problem. That is the reason why they have it. And then lever X. So what do? Initially they move it vertically up like shown here. They are moving it up like that. Then what they are doing is, then they move the lever horizontally back and forth this way. Horizontally they are moving it back and forth. That is the first change. Then this is the second movement. So initially they move it up, then they observe the galvanometer, then they move it like this back and forth and they observe the galvanometer. That is the activity. So the first question, what will be the observation in the indicator of the galvanometer when the lever is moved as mentioned above? So what do you all think? Now the magnetic field is this way. Now this is the electromagnetic induction, Fleming's right-hand rule. All three factors have to be perpendicular. Now the current will flow through this. Magnetic field is this way. So you can see magnetic field that way. Let's say if there is current flowing, we'll assume that there is current flow. That's either going to be this way or that way. That you can understand. So then the movement, let's say if you have your hand like this, magnetic field is the second index finger. Let's say current is this or this, it doesn't matter. But the current is, let's say, flowing in this direction. So the movement should be perpendicular to that. So then if they move the lever up, pull the lever up, this copper rod also moves up. So the movement is perpendicular to the rod as well as the magnetic field. So then there will be an induced electromotive force, current will flow through it. So in the first instance, it's possible for a current to flow. So then you will see a deflection in the galvanometer. But in the second instance, now here you can see the copper wire, copper rod is this way, and it's going to move like that. So the current has to flow through the copper conductor, and the movement is also parallel to that or in the same direction. Then of course there will be no induced electromotive force. Therefore, there will be no change in the galvanometer. So in the first instance, when the lever is moved vertically up, you will see a deflection in the galvanometer. But in the second instance, there will be no deflection. That is what you need to write here. Move the lever vertically up, deflection in the galvanometer. Here, no deflection, that is move the lever horizontally back and forth, no deflection in the galvanometer. Is that clear, student? So then I'll move on to the next part of the question. The second part, mention the reasons for the above observation. So first one, direction of movement, magnetic field, and the conductor are all perpendicular to each other. Therefore, EMF is induced. In the second one, we have to say direction of movement is parallel to the conductor. Therefore, there is no electromagnetic induction. So in the first instance, when the lever is moved upwards, all three are perpendicular. Direction of movement, direction of magnetic field, and the conductor are all perpendicular to each other. Therefore, electromotive force is induced. So you will see a deflection in the galvanometer. But in the second instance, direction of movement is parallel to the conductor. So through the conductor only current should flow. Then they are both parallel. Direction of motion and the direction of current are going to be parallel. So therefore, there will be no electromagnetic induction. Is that clear, students? So then I'll discuss the next part. Name an equipment that functions based on the above principle. Equipments that function based on electromagnetic induction. You all are familiar with this, the alternating current dynamo, the bicycle dynamo, the moving coil microphone, then the transformer. You can write any one of them. Name an equipment that functions based on the above principle. So I will write moving coil magnetic microphone. Moving coil magnetic microphone. So you're familiar with the dynamo, the normal alternating current dynamo, the bicycle dynamo, then even the transformer. All of them function based on this. Even the magnetic cards, the bank cards, debit cards, credit cards, even the employee cards, they also use the same principle, electromagnetic induction. So, one equipment, moving coil, magnetic microphone. So, with that students, I'll move on to the next slide. So, here the last question, extra question 20. The diagram shows a model of a direct current, that is DC motor. So, if we look at the motor, here you can see the north and the south poles are indicated. So, the magnetic poles, they are labeled as P and Q there. Then you can see the wire loop A, B, C, D. They have shown two directions for rotation, X and Y. So, maybe we'll have to identify the direction. Then here you can see the end A is connected to a split ring R. Both rings are labeled as R, so split rings. The other split ring is connected to D, and the brush is shown as T, and here we have the power supply. So that is the DC motor, a model of a DC motor. Then you can look at the question. State whether the magnetic field in this setup is from P to Q or Q to P. So there you can see magnetic field P and Q. N is the north pole, that is P. So that means magnetic field is going to be from P to Q, that is north to south. So here it is P to Q. Then the second question, name R and T. What is R? Here you can see split rings. So R is split rings, and T, already I told you all, the brushes. There. Why is it required to break R into two parts? Why does it have to be split rings, not a continuous ring? You know the reason. Then only the current flow through the wire loop will be altered. The direction of the current flow through the wire loop will be alternate. So then only the loop will rotate in the same direction. So that is the requirement why the R is split into two. So you can say the split rings alternate the direction of current flow through the wire loop, that is A, B, C, D and D, C, B, A directions. This is possible when the rings are split. So only when you have split rings or two parts, then only you can alternate the current. So you can remember that we have discussed the function of a direct current motor. So why is it required to break R into two parts? Split rings alternate the direction of current flow through the wire loop, that is ABCD and DCBA directions. So this is possible when the rings are split or when R is broken into two parts. So you can say R is broken into two parts. So that is the split rings. I'm sure you all can understand that, students. With that, I'll move on to the last slide. Fourth part, state whether this motor rotates to the side of X or Y when current is applied. So there, what do? You use the Fleming's left-hand rule. So here you can see this is the positive terminal, negative terminal. So here the current will flow from A to B. So if we apply the Fleming's left-hand rule for that, you can see the field is from north to south and the current flow is going to be into the board. So it's going to be this way, north to south, the field, current is flowing from A to B. So the direction of the force is down. So this side, the force will be down. The same way, just to confirm, C and D, current flow is outwards. C to D, field is from north to south, so the movement is up. So here, the force is upwards. So then you know the rotation is going to be that way. That is direction Y. So here. State whether this motor rotates to the side of X or Y. Side Y. Y. Or you can just write Y. Fifth one. What happens to the direction of rotation of the motor when the current direction is reversed? If you change the direction of the current flow, the rotation changes. So here, rotation changes to direction X. So there, X and Y, rotation will change to direction X. There. Select from A, B, B, C and C, D the conductor on which the magnetic force does not act. You all can remember that. I have explained that to you all before. So the direction of current flow through AB and CD is perpendicular to the magnetic field. At the same time, the magnetic field and the direction of the current flow are perpendicular to the direction of the force. Therefore, there is a force acting on both AB and CD. But if you consider the side BC from here to there, like I told you all, north to south is the magnetic field. That is going to be this way. At the same time, the BC conductor is also in this direction. So, magnetic field lines and the conductor are parallel to each other. The conductor BC and the magnetic field lines are parallel. So, because of that, there will be no force acting on the conductor BC. You have to remember that. So, here, select from AB, BC and CD the conductor on which the magnetic force does not act, BC. BC. Is that clear, students? You have to remember all three have to be perpendicular. We hold the hand this way. Direction of the current, direction of the magnetic field, direction of motion. Everything has to be perpendicular. If the magnetic field and the conductor become parallel, then current and magnetic field become parallel like that. So then there will be no force acting on it. So that is why BC conductor there is no force acting on it. Then the last part, write the reason for your answer in part 4. Part 4 is the fourth part up there. So there you can see, state whether this motor rotates to the side of X or Y when current is applied. There, of course, it is in the Y direction that we found using the Fleming's left-hand rule. So there we can say, when Fleming's left-hand rule is applied, conductor AB, so there you can see force is downwards, CD force is upwards. So we can say, when Fleming's left-hand rule is applied, the force acts downwards on conductor AB and upwards on conductor CD. Therefore, it is an anti-clockwise rotation in the y direction. So that is how we explain. You can see that here. So the force is downwards on AB, upwards in CD. So the rotation is going to be anti-clockwise. So that is when you apply the Fleming's left-hand rule. So it is towards side Y. That is what I have explained here. When Fleming's left-hand rule is applied, the force acts downwards on conductor AB and upwards on conductor CD. Therefore, it is an anti-clockwise rotation in the Y direction. So that is the question. Those are the parts of the question related to the direct current motor, students. So far we have discussed many different questions, although they were mostly related to either the motor or the dynamo or the transformer, but all the questions were different to one another. So I am sure now you all are competent enough to answer any type of question related to electromagnetism. So with that, I have come to the end of this chapter, and also for that matter, I have completed this lesson, electromagnetism. We discussed the theory related to electromagnetism, and thereafter we discussed the questions given in your textbook and also so many extra questions. So I am sure, students, you all are competent enough to answer any question related to this particular lesson.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.